Okay, so now we're going to try and connect what we've done to the fast Fourier transform, that expression, that the Fourier series to the fast Fourier transform. So let's just go and have a look here. What we had was we found that Cn hat naught, the initial value of Cn hat was this expression here, 1 over 2L, the integral from minus L to L of e to the minus I kn x C naught of x dx. All right, now we're going to try and we're going to do this integration by the very simplest possible method. So we're not going to use some fancy method, we're going to do it by the midpoint rule. So we're going to set up, we've got to go from from minus L to L, so we're going to set up a series of points, quadrature points, which I'm going to call xm, which run from minus L to L. So we get 2L over n times m. Okay, so we've got there's a discrete set of points running from, so m equals 0 dot 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 to n. And we're not going to use the last one on our quadrature, right? Because we'd end up we'd count that twice somehow, right? And we probably should use the midpoint, but we're actually using the left-hand side point, but it doesn't really matter which one you use, it makes no difference. You can try it yourself. Okay, so there's a discrete set of points. So then we're going to write this integral here as approximately 1 over 2L times the sum of e to the minus I kn times xm c naught of xm times this weighting function, which is 2L over n. And it's the sum from m equals, okay, 0 to n minus 1. Okay, brilliant. So that, change colour. Okay, so that's, and this is now a vector. C naught of xm is now a vector, it's a discrete set of points. So we've sort of gone to something that's taking a vector and it's mapping it to another vector in a sense, because we've got the discrete set for kn. So just recall here that kn is equal to n pi over L. Okay, so if we carry on with this, we can cancel the two L's out and we get xm is minus L over 2L over m, and kn is m pi over L. So we get 1 over n times the sum n equals 0 to n minus 1 times e to the power of, and now when we work this out, we get minus I n pi over L multiplied by minus L plus 2L over n times m c naught of xm. And then a lot of cancellations happen here. So all the L's cancel and we get 1 over n, the sum from m equals 0 to n minus 1. So we're summing over this is just the discrete sum calculating the this integral. So what happens here, we get e to the I in pi, and we get e to the power of minus, it's going to be 2 pi I n times m over n, which is almost identical to the, this is actually, with the 1 over n, this is the inverse Fourier transform formula, minus this term here. Okay, we've got this extra bit, and that's floated in because of the fact that we chose to do the left-hand endpoint. So we'll see that it cancels out when we go back anyway, it doesn't matter. All right. So now we've got to go back and work out what is the actual solution C of, now we've got a discrete set of points here that we're calculating it at, aren't we? Right? So this is going to be the sum, going back to our formula that we had before, it's the sum from n equals minus infinity to infinity of c naught hat of x naught, c naught hat of naught times e to the minus kn squared tb times e to the I knx. All right. So now we substitute this expression here for C naught. Sorry, we substitute the expression for Kn, right, that we had before, n pi over L, and then we end up with the sum from n equals minus infinity to infinity of C naught hat of naught e to the minus kn squared td, and then when we substitute that in here, we're going to get, times x m, we're going to get exactly this 2 pi I n m over, it's going to be positive, and we're going to get it multiplied by e to the power of minus I, right, from this minus L minus I n pi, okay, which cancels out the one we had here, okay, C naught times e to the minus I n pi will exactly equal that. So we've now got the, and this is almost identical to the difference between the fast Fourier transform and the inverse Fourier transform is this plus becomes a minus and the 1 over m appears in the inverse Fourier transform. So we've almost, just by doing the simple quadrature, okay, we've still got the sum from going minus infinity to infinity, but that's going to turn out that there's no point doing that sum. You know, you just reduce it, you only get otherwise you start mapping around and you don't get anywhere because of the discrete nature of these x's. But we've basically shown here how the solution could be implemented just by using a fast Fourier transform to do the quadrature for us. Okay, and all the quadrature terms just appear and disappear and sort of cancel each other out with